Morning. Good morning and welcome back to Classical Mechanics 1 at CMI. This is our 11th meeting, 28th October, Thursday, 2021. While we wait for the others to join us, did I have a question from Siddhansha?
Yes, sir. Sir, I wanted to ask, when are you planning on taking the mid-sems? Because like three of our subjects will be done before Diwali.
3 of you will be done. What does that mean?
3 of our subjects, analysis 1, algebra 1, and English, will be done before Diwali. So just classical mechanics and CS will be left. So I was just asking.
Okay. So currently, I have not planned a midterm exam. We will, at present, I am planning to give additional assignments. So that is the current status. If there is any change, I will let you know.
Okay, sir. Thank you.
Thank you, sir. Yeah. This plan sounds great.
This is Anand Balivada is overjoyed. Okay.
So the assignments are fun.
Okay. Yeah. I think they have been not fairly simple, would you say? I mean, or at least not excessively complicated.
Yeah, I mean, I don't want to say anything that might like later come back to haunt me, but rather than commenting on the difficulty, definitely was able to learn things from doing the problem sets.
Okay, fine. That is the main objective. Yeah.
Excuse me, sir.
We shall continue that. Yes, I have a, sorry, who is speaking?
Shubham Kumar.
Yes, please.
Sir, I had a doubt, a small doubt.
Uh-huh.
Sir, I mean, when we say that force is equal to mass times acceleration, the second law, it incorporates the Galilean principle of relativity. But if we write the force equation dp by dt as dm by dt into r dot plus m into r double dot, then how do we incorporate the Galilean principle? There I had a small doubt.
Okay, I lost you in the middle, but you're saying instead of writing it as r double dot, or mr double dot, you're saying suppose you write it as p dot. Is that what you're saying?
Yes, sir. And then we do not consider mass as constant.
Oh, no. Mass is not constant. Mass of particle is constant. So there is no confusion about that. If that is what your question is, we will declare that, and this is what is observed, that masses of particles do not change with time. It is a completely different matter if you want to describe some composite system which is losing some material and so on. Then you have to deal with that separately. That doesn't mean that Newton's second law is violated. Masses of point particles do not change with time. And mass is neither created nor destroyed. So, yeah.
Okay, sir.
Yeah, I mean, is that the import of your question, or is there some other aspect that you're writing it as first order rather than second order? What was your...
Yes, I mean, like if we write that the equation in that form, then how will it be Galilean? How will it incorporate the Galilean principle of relativity? That I was not understanding.
Yeah, but no, the Galilean principle of relativity concerns uniform motion. So that would, this is just some slight rewriting. You're writing P dot as
yes,
P as mr dot, and then P dot is equal to force. So the same arguments we made will apply here too. It is the very same equation. So you can't get something different over here.
By the way, sir,
and if you, in other words, if you make a boost, that is, you go to a frame which is moving at constant speed, one should be able to show that the solutions you get in one frame are the same as the solutions you get in another frame. Trajectories are identical. Whether you describe the trajectories using r of t or through an intermediary called p of t and then r of t, it doesn't matter. The question really is, are trajectories identical? And that is guaranteed by Newton's second law in two frames that are in uniform relative motion. Does that partly address your question,
Okay.
Shubham?
Yes, sir. I mean, yes. If we like, I tried it. Like, I wrote that equation and I transformed it, but like r dot term will, I mean, it won't get removed. That's why I asked. Can you like just
Okay.
show the working of that?
Okay, let me try to address this in a proper way. I will try to work out and
Okay, sir.
yeah, that might be better. Yeah, so that you want to see the details addressed. Okay, I'll try to do that. Sure. Let me. Okay. Yeah. So we now have nearly 40 people with us, and perhaps another 20 to join or so. Okay, so let us nevertheless get started. Are there any further questions at this stage? I mean, I do intend to clarify some things from last time, so that is coming up, but please go ahead.
So when we say that force is acting on a system of particles, we say that force is acting on the center of mass of the particle system.
No, we don't. Like you could have a composite body. In fact, I plan to speak about this in a moment. You could have a composite body like this bottle, which is made of many particles, and the gravitational force acts on each of them. We don't say that the force acts on the center of mass. No, there are certain purposes for which it is convenient to introduce a center of mass and look at the motion of the center of mass. And that's a separate matter, and we will do that. So I would be very hesitant to use the statement that the force acts on the center of mass. The force acts on individual particles. Yes, one can talk about the total force on the composite body. That is a meaningful question, and I will speak about that. But yeah, one has to be very careful about these statements because they will likely mislead you.
Yeah, fine.
Yeah, sure.
Thank you.
Okay. Okay, so I am. We are joined by our TA Vishnu Kadiri as well. Yeah. Okay. So if there aren't any further questions, I will share my screen. Before we continue, I had wanted to mention a couple of things from last time. Yeah, I paraphrased Galileo's book title. And the correct title is, I think, a dialogue concerning the two chief world systems. I creatively used some synonyms for some of those words. That is still a short title. The full title is even longer. He is extraordinarily careful. He even says in the title that something about inconclusive results about these things. He is extraordinarily careful. That he finally says that this dialogue is inconclusive as well, so, something to that effect. So yeah, anyway, I misspoke when I spoke when I mentioned the title of the book slightly. I paraphrased some of the words. And I think I also mispronounced the name of the person who speaks for the heliocentric Copernican viewpoint. The name is Salviati. I think I mispronounced it last time. Yeah. In addition, problem set 4 is due tomorrow, 6 p.m. Friday, tomorrow evening. So please do submit it well in time. I think last time there were some more questions, which I intend to address right now. So let us get started. Yeah. Okay, so just to, I want to recapitulate some things from last time. We did, in particular, I want to address this question about higher time derivatives in the equation of motion, that is in Newton's second law equation, which was something that I think Shubham Kumar and somebody else,
Ripunjay.
Ripunjay Dwivedi, yes. The two of you had raised some questions about that. Let me, I want to make some very brief comments about that. Let us proceed to that. So as I said, relating the force to the second derivative of position as opposed to the third derivative is the simplest way of incorporating Galileo's principle. Yeah. And I think we are in agreement on that. I mean, the third derivative would also work in the sense that two frames that are in uniform relative motion would have identical equations of motion. Basically, the three derivatives will kill the ut term where r prime is equal to r minus ut. Okay, and as I also pointed out, experiments confirm Newton's second law. At least they are consistent with the predictions that come from Newton's second law. So, so there is no need to include higher time derivatives. Yeah, although they would not violate Galileo's principle. Yeah. However, there are other reasons to avoid this. Okay, one second. I think I have to change some setting here. Yeah. By the way, a pleasant observation. Oh, perhaps it's not so pleasant after all. Yeah. I thought that this peculiar feature of 9:41 a.m. on the 9th of January had gone away, but no, it is very much there. It's too bad.
Yes, it went away from the previous few classes, like correct date was shown.
Yeah. So, okay. So yes, you have observed the same thing as I did. It did go away. Now it is back. Okay. I don't know. Maybe I'm doing something peculiar as well. Okay. Yeah. Now, as I was saying, there are other reasons to avoid higher time derivatives on the left-hand side of Newton's equation. Let us take a concrete setup. Suppose Newton's second law for the position x of t, let's just focus on one dimension, x of t of a particle moving along a line had a third derivative term. Okay, so we are considering now that modified equation mx double dot plus a new term called mu x triple dot equal to the force. Okay, so this is our proposed modification of Newton's second law. Yeah. And let us see what consequences accrue from this. Of course, nu is not zero. If nu was zero, you come back to usual Newton's second law. And F is some force. Now, let us consider free particle motion, that is in the absence of any force, F equal to 0. Then the equation is now a third order equation, mx double dot plus nu x triple dot equal to 0. Yeah, this equation admits the solution x of t is equal to a quadratic function of time, namely half alpha t squared plus beta t plus gamma. Yeah, we can write this. This is a solution of that equation. Yeah, you will see that the third derivative will kill this alpha t squared term. Yeah, so and we can take alpha non-zero. This is a valid solution. However, this solution violates Newton's first law, because it says that this free particle trajectory does not have constant speed. Indeed, the speed of this particle x dot, if you differentiate this formula, is alpha t plus beta. Yeah, so the velocity is not independent of time. In fact, it is time dependent because alpha was not zero. Yeah, so higher order equation violates Newton's first law, though it is consistent with Galilean principle of relativity. Okay, so I hope this provides some justification as to why we avoid higher derivatives. There are other ways to think about it, of course.
Sir, not having constant speed implies that the body cannot have constant speed at any instant of time. I mean, if alpha is not equal to 0, then for a body it is not possible to attain constant speed, and that's what violates Newton's first law, right?
Correct. Yeah.
Okay.
So this is a solution. You're quite right. Of course, the correct statement is that constant velocity, you can have constant speed. Yeah, but I mean, constant speed is a particular case. It certainly has to be true. If you have constant velocity, your speed has to be constant, and that is violated over here. So Newton's first law required that free particles must have constant velocity, and in particular constant speed. And here is a solution of free particle which doesn't have that feature. And I didn't talk about velocity because it's in one dimension. So there is, I mean, everything is in the x direction. So I didn't write boldface and x hat and so on. So that was Neelabja, right? Is that okay?
Yes, sir.
Okay, good. Okay, so I hope this at least removes some of the questions from, I mean, addresses some of the questions from last time, especially from Shubham Kumar and Ripunjay Dwivedi. Yeah.
So how is the solution of x is equal to half alpha t square plus beta t?
Okay.
Like
how did that solution come? Well, okay. Let's just go back to the equation of motion that was proposed. Yeah, we are considering a modified Newton equation, namely mx double dot plus nu x triple dot equal to the force. Okay, the question is, can you somehow give an argument why this third derivative term should not be present? That was the question. So let us suppose it is there and arrive at a contradiction. That is our strategy. In particular, let us consider a case where the force is absent, namely a free particle. Yeah. Now, somebody takes this equation and I write down a solution of that equation. I mean, you can check it, right? Suppose you calculate x dot, then x dot is equal to alpha t plus beta, right? Simply differentiating. X double dot is equal to alpha and x triple dot, have I, oh, I am sorry, did I make a mistake? Yeah, I have made a mistake. You're saying that it's not a solution.
Yeah.
Okay, yes, because the second derivative term will produce something here. Correct. Okay, yeah, I'm sorry. This is not a solution. Sorry, this is not a solution.
I think it should be cubic to have.
You're right. This is not a solution. But I'm sorry, I have oversimplified the argument. What one has to do is take this equation, and I mistakenly wrote this formula without checking it properly, as you have pointed out. But the point is that this equation has solutions which do not have constant velocity, and that is something one has to show. So, okay, I have not completed the argument here. Yes, Shakti Chauhan has correctly pointed out that I have a calculation error here. So we really need to solve this equation, and that needs to be done with some care. You can integrate once, you will get mx dot plus nu x double dot equal to 0, plus is a constant. Yeah, I guess I will not go through the full thing here, because this may take a bit more effort. And then you integrate once more, mx plus nu x dot is equal to c1t plus c2. All right. So now this is a first order differential equation. First order differential equation. And you could integrate it once again. I mean, you cannot do it explicitly. You have to, this is inhomogeneous equation. There are ways to do this. But we will, perhaps I will discuss this in more detail another time. But the point is to again deduce some contradiction, that that the speed is not a constant. I mean, it may be already somewhat plausible here. We have computed the speed in effect. X dot is this thing minus mx. It is plausible that x dot is not 0. Sorry, x dot is not a constant. Because there is some time dependence already here, and there is this mx term here. One has to deal with it. So okay, I stand corrected. My proposed solution is not a solution. Yeah, so let me cross it out. but a little bit more effort will be needed to show that this equation has solutions that don't travel at constant speed. Okay, is that so? This discussion is not complete. I admit that. Sorry, I used the word admit because I was trying to admit somebody to the class. I acknowledge that. So I'll try to simplify this and clean up the argument next time. But this is the idea that that I believe would be fruitful in addressing this question. I mean, any question about the overall idea as opposed to the calculation? Okay, fine. All right. Then we also addressed last time another question was whether the left-hand side of Newton's equation could involve a term such that such as lambda r itself. Okay? See, we've talked about derivative terms, but what about non-derivative terms? Simply the vector r itself. Yeah. And the answer is again no. You can't have such a term for more than one reason. This would violate Newton's first law. Once again, I am trying to use a similar argument. Free particles, that is, if you replace the force with 0, free particles would not always follow straight line trajectories with constant speed. Indeed, suppose lambda were non-zero, then the equation of motion would say mx double dot plus lambda x equal to 0. Yeah. Now, the straight line constant speed solution that you want, I mean, a constant speed trajectory must be of the form x of t is equal to vt plus x naught. Yeah, but unfortunately, that is not a solution of this equation. If you put it there, it is the first term will go away, but the lambda x term will remain. So it is not equal to 0. So Newton's first law would be violated if you have a explicit position term in the equation of motion. Is this calculation acceptable? That is, have I not made a mistake? Perhaps a similar argument should be used in the previous case. Okay, but I do need to fix up the previous argument. Yeah. Last time I gave a different argument, which is also valid, that having an explicit position dependent term in the equation would violate the homogeneity of space, which requires that the laws of mechanics be the same at all locations. What I mean by that is that given the same external conditions, the results of mechanical experiments, same external conditions, that's quite important. The external conditions vary, like the acceleration due to gravity is different in two different places, and you are doing an experiment that involves that, then you cannot expect to get the same answer. But suppose external conditions are the same, then mechanical experiments do not, the results of mechanical experiments do not depend on where they are performed, here or in a different city. Yeah, and we went to, yes, I have a question. Okay.
So basically, I just wanted to. I actually joined 10 minutes late due to some network issue.
Okay. Who is speaking, please?
So I just wanted to confirm we are fine. Am I audible?
Yes. There is some background noise.
So I wanted to ask that basically what we're saying. So I'll try to get to a new location. Just a minute.
Yeah. So may I first? Yeah. There is some feedback, I think, or some disturbance. But yeah, please speak up. That's okay. Okay, we seem to have lost you. Okay. Okay. Ripunjay, are you able to hear me? Fine. Well, when you do get back, please re-ask your question. Okay. So, as you were saying last time, mathematically, when I talk about this homogeneity of space simply means that all locations are on an equal footing. There is no distinguished location subject to the same external conditions. And mathematically, that is the requirement that Newton's second law equation must be translation invariant. That is, if we make a translation x prime is equal to x plus a is a kind of constant shift, then the equation should not change. Unfortunately, this equation that we wrote down with an explicit position term is not invariant because x will go to x plus a, whereas the x double dot term will kill the a constant. So the new equation in the shifted frame will be x prime double dot plus lambda x prime minus a equal to the force. And unfortunately, that's not the same as the original equation. So Newton's equation would not take the same form in a frame that is shifted by a distance a relative to the original frame. Yeah. So this is called, this is the requirement of translation invariance or homogeneity of space, and that would be violated if you had an explicit position dependent term in the equation of motion on the left hand side of the equation of motion. Of course, interparticle forces are translation invariant because they depend on the relative locations of particles. That is the displacement between two particles, or usually the magnitude of the distance between two particles, displacement between two particles. So if you displace both particles, then the distance doesn't change and translation invariance is maintained. Okay. Any question about what we've spoken about right now? Okay. All right. Then I wanted to continue in this vein. We have talked about spatial homogeneity, no distinguished location. Similarly, we also postulate the laws of mechanics do not pick out any particular direction. Yeah. There is no distinguished direction. We say that space is isotropic. Isotropic means all directions have the same properties. So to say it differently, the orientation, namely the angular orientation of a frame, should have no dynamical significance. If you rotate your frame, the physics you describe in the rotated frame and the physics you described previously should be one and the same. Or to say it in a more operational manner, holding external conditions fixed, provided external conditions are the same, rotating the experimental apparatus does not change the results of experiments. All right. Rotating the experimental apparatus should not change the result of the experiment. It's very important to bear in mind that external conditions must be the same. If your apparatus is studying something about gravity, which points only downwards, which is an external force, then of course it will matter. If you rotate your apparatus, then gravity will point in a different direction and the behavior of the system may be different. So that is not what is meant. What is meant is that holding external conditions the same, if you rotate your apparatus, the behavior of interparticle motion within that system should not change. Okay, so this is called the isotropy of space or rotation invariance of the laws of mechanics. Yeah. So now, along with homogeneity and isotropy of space, okay, there is a question in the chat. Aha. Okay. Okay, Punjay Dwivedi has a question. Okay, let me, since I moved on to a slightly different question topic, let me come back to this. I think his question is still about this question about the order of the differential equation. Yeah, let me come back to that. I'll go through what he has written and address it afterwards. So please bear with me, Punjay. Yeah. And I was not able to hear your question. So anyway, coming back to this issue of translation and rotation invariance, along with homogeneity and isotropy of space, we also postulate the homogeneity of time. Homogeneity of time means is also called time translation invariance. So what that means is that given identical external conditions, the results of mechanical experiments must not depend on when they are done. You must be able to reproduce the results you got today when you perform the same experiments 3 days from now, provided the external conditions are maintained. Stated differently, in other words, the equations of mechanics must be invariant under translations of time. That is, changing the origin of time. T goes to t plus t naught. The t naught should drop out from the equations of motion. It should not appear in the equation of motion. If it did, then there is something. Then the equation does not respect time translation invariance. Yeah. For instance, the masses of particles that interact through certain forces, interparticle forces, cannot change with time. That's not all. I mean, many things cannot change with time, but masses in particular do not change with time. Okay, so basically we've talked about several invariances. Space rotation invariance, yeah, angular orientation of the frame doesn't matter. Space translation, translating the frame from here to there should not affect the equations of motion. Translating time, changing the origin of time, zero of time, all of these must be invariances of the equations of motion. They must be symmetries of the equations of motion. And along with the invariance under a change from an inertial frame to another frame moving at constant velocity. So this is what we began discussing. So it's Galilean invariance, yeah, or Galilean boost. Yeah, so we have now talked about several transformations, rotations, translations of space, translations of time, and finally passage from one frame to a uniformly moving frame relative to it. Together, these are called the Galilean invariances of the laws of mechanics. Okay. Of course, Galileo only focused on passage to a frame moving at constant velocity, but all of these together nowadays are called the Galilean invariants of the laws of mechanics. So that is a terminology that is worth bearing in mind. Okay, any question about these statements? All right. If not, let me quickly recall what we said about the linear superposition of forces. Had a couple of comments on that as well. So this is the linear superposition of forces principle. So suppose a particle is acted upon by two forces, F1 and F2. Then according to this principle, the total force F on the particle is the resultant of the two forces. I mean, it's also called the resultant, and it is equal to the vector sum F1 plus F2. Okay, so this is something you are familiar with from last time. This is to be expected from Newton's second law, for consistency, because acceleration is a vector, so force must also be a vector, and vectors can be added. And they can be added using the parallelogram law to obtain the total force. So it can be regarded as a consequence or a consistency feature from second law. And indeed, Newton does not mention the superposition principle for forces as a separate law, but he states it as corollary number 1 in the mathematical principles of natural philosophy. So yeah, but it is often helpful to give it a name, superposition principle. And as I was saying last time, of course, I mean, Newton combined lots of experimental results and theoretical ideas and distilled them. And this took a long time. Even Newton himself, it is noteworthy that he had more than 3 laws, in fact, about 5 or 6, depending on how you count them, in his manuscript. And last time Ripunjay asked the name of the manuscript. It is called De Motu, the full name is De Motu Corporum in Medis Regulariter Sedentibus. Yeah, so this this Latin name is the title of Newton's manuscript, which he wrote a couple of years before the Principia. And in this, it was still not in the final, at least not in the same state as the Principia. Some laws and postulates that he had over here, including a version of the principle of relativity, were later demoted or switched to corollaries of what we now call his 3 laws of motion. Yeah, so that is also the case with the superposition principle. Yeah. Okay. Needless to say, any question about that? Yeah. So needless to say, the superposition principle is very useful. It allows us to separately determine individual forces on a body, which may have distinct physical origins. They may be gravitational, electric, frictional, and so on, before adding them up to find the total force. Okay. So, but you do need to add them up before solving the equations. You cannot solve the equation for each force separately and add the solutions. This doesn't work. So that is what I said at the very end last time, that we do have a superposition principle for forces, but we do not have a superposition principle for solutions of Newton's equations in general. Okay. So let me just state this in a little bit more detail. So for example, suppose a particle is acted upon by 2 forces called F1 and F2. Okay. F1 and F2. F1 may be the gravity force, and F2 may be some electric force, something like that. Yeah. Okay. So now suppose you have solved the equation of motion just with gravity present separately and with F2 present separately. Yeah, and you find a pair of trajectories, R1 of t and R2 of t. So these are trajectories in the presence of individual forces. Yeah. Now suppose we do the following. Basically simply add the 2 equations. I mean, the equations are valid, so you're free to add them. So you will, and let us denote R as R1 plus R2. Okay. Then you will get the equation mr double dot is equal to F1 of R1 plus F2 of R2. All right. So this is valid. It's just arithmetic. So it is true. However, we can ask the question, is this R, namely the sum of the 2 trajectories, is it a trajectory when both forces are present? Yeah, because that is what we are really after. And the answer to that question is generally no. It is not a trajectory when both forces are present. Okay, that is because F1 of R1 plus F2 of R2 is generally not equal to the vector field F1 plus F2 evaluated at R1 plus R2. Because that is really what you want. You want to know the trajectory in the presence of both forces at a particular place where is at a particular instant of time, where is the particle when both forces are present. Unfortunately, F1 of R1 plus F2 of R2 is not equal in general to F1 plus F2 evaluated at R1 plus R2. Okay, so one can show this by providing a counterexample. Yeah, and if you are keen to see a counterexample now, I shall provide it, or I shall give it as a question in the assignment. Maybe I will do the latter so that you get some practice and creativity in the process. Yeah. So anyway, this is the assertion that you cannot add trajectories in the presence of individual forces to get a trajectory when both forces are present. Any question about the statement? Yeah, somebody had asked me to state this clearly last time, so that is the reason. All right. Yes.
I understand how you are putting R equals R1 and R2, R1 plus R2. I mean, you're taking forces as an invariant a function of position.
Yeah, the force is a function of position, indeed. Yeah.
Okay,
Look at it this way. I have a particle here, a mass. I have the sun here and the moon here, or just two massive particles somewhere else. Each of them produces a force acting on my mass or satellite. The question is, can I find the trajectory of the satellite in the presence of both the sun and the moon if I know its trajectory when the sun is absent and when the moon is absent? Answer is not quite. You can't do that. Okay, that's the physical setup. But please ask your question again.
So I'm not sure, like, so when you're putting R is equal to R plus R2, so R1 is the position that would exist on the trajectory if one of the forces is absent.
Yeah.
And R2 is another position that will exist on the trajectory if another force is absent. So I don't see how we're adding these positions up.
Yeah.
I mean, this is the case in which it holds. So, I mean, you're saying that the first one is what we get when we add up the forces by superposition.
Yeah.
I don't see how you're adding the position vectors to get another vector and then saying F1 R1.
Okay. No, okay. The question is, can we by some procedure combine these two equations, which are true? We have solved these two equations. The question is, can we somehow combine these two equations to get a solution when both forces are present? And the answer is no. So whatever I am doing here doesn't work. All right. So if that is your concern, you are fully justified. This doesn't work. So that is the final story. But one can see how far it goes, right? The two equations are valid. You can add the two equations, get one equation. If you are lucky, the equation will at least make sense in the sense that R1 and R2 may be addable. Yeah, they are vectors in some three-dimensional space, so maybe you can add them. So at least you can make sense of that quantity. Yeah, and the forces again are vectors. Maybe you can add them, make sense of that quantity. The question is, does this equation anyway resemble or is identical to the equation of motion when both forces are present? And that latter question has the answer no. Yeah, so you are yes, once again, yes.
Expressions on the right hand side are just the approximations of the values of MR1 or MR2.
Okay, Romit Roy Chaudhary says that clarifies my problem, I think. Thank you. Okay, so now we have a question of Debashish Bishwal. Please once again.
I guess the expressions on the right hand sides of both MR1 and MR2 are kind of the approximations of those values. I mean, by a function that approximates MR1 and another function F2 that approximates MR2. We could also have even more stricter function that would evaluate both of this MR1 and MR2 to even a greater extent.
Wait. I think, I mean, you're thinking about something slightly different. I would like to emphasize what we are trying to do. We are trying to do a very concrete physical thing.
Sir, am I wrong in this giving this statement?
I'm sorry, I'm not able to understand your statement very clearly. As you are speaking of something as an approximation to something else and so on. Yeah. I'm not sure. I catch that. We are asking a very simple question. Forces can be superposed to get the total force. Can you similarly add up solutions?
Yes, sir. Because I read somewhere else there are even some other terms. You could add some other terms to these terms on the right hand side to make it more elegant. I mean, to make it more approximate to the value on the left hand side.
Okay. Okay. I have not read that thing that you referred to. So I would have to understand it better to answer your question. But okay. Okay.
No,
so
it's fine, sir. I'm sorry.
Yeah.
I'm sorry. Sir.
Yeah, that's okay. That's okay. No problem. Yeah. Okay. So, but okay. I think maybe it will help to really give a counterexample. Let me do this. Yeah, I'm thinking of giving this as a homework, but here we go. Let me suppose that the first force F1, yeah, is some kind of gravitational force. Yeah. So F1 is a force that points in the direction of this vector R. I mean, I've just written it here as R1. That is not relevant. Okay, so F1 is a force of this sort. So this is a force, let us say, due to the moon on any particle, which is located at the position R. Similarly, the force due to the sun may be given by some beta times R by mod R squared. Okay, this is what the force due to the sun is on the same particle. All right, the sun has different mass than the moon, so maybe alpha and beta are not the same. Okay, then we suppose that we have solved the equation of motion when the moon alone is present and the sun alone is present. In other words, we have these two equations satisfied. All right. Now the total force when both sun and moon are present is F1 vector plus F2 vector. All right, and what is that total force? I'll call it a capital F. That is, the total force at any location is given by alpha R upon mod R squared plus beta R upon mod R squared. Okay, this is our proposal. I mean, this follows simply from the superposition principle. This is the total force. This is the force for which you need to find trajectories. Yeah, that is the overall aim. Now we ask the question, can we be lazy? Can we somehow use the trajectories when the moon alone was present and sun alone was present to somehow combine those trajectories to get a trajectory when both are present? Well, the simple-minded way to do that does not work. So suppose,
Sir,
yes. Yeah.
Sir, I think, Shubham Kumar.
Yeah.
Sir, I think you should, I mean, you should use R1 and R2 because they are the distance from moon and the sun. So 1R will not work, I think.
Okay. Well, I would like to clarify that. Okay. All right. So let us say, okay. So maybe see, I have simply made some forces up. All right. Maybe I used the term sun and moon and so on just as a way of providing some kind of context. R is the position vector of the particle.
Yes, sir. So
yes,
it should be alpha r divided by r minus r1 mod whole square plus beta divided by r minus r2 mod whole square, where r1 and r2 are the sources of the two gravitational force.
Okay. Okay. Perhaps. All right. I think you have you are trying to set this up in a more careful way. Yeah. Okay. One could try to do that, perhaps. I'm not sure it is going to change the conclusion. Okay, so okay, let me just finish the argument I was making and then come back to what Shubham has said. Maybe this requires some more details, but the point is that this F, this is the total force, sum of the two forces. See, I think Shubham, you are thinking of the sun and the moon at two different locations. Yeah, and you're thinking of that very specific physical context, and that is excellent. That was just a metaphor for me. All I was saying is that there is a particle that feels two forces, one which is given by this formula and one that is given by that formula. It's a particle that feels two forces.
Okay, sir. Okay, I got it.
All right, great. So my metaphor of the sun and the moon is not to be taken too seriously. A particle simply feels two forces, this one F1 and that one F2, if it is located at a point R. That's all. R is the location of the particle relative to some origin. That is entirely up to us. Now, suppose you have solved the equation of motion in the presence of each of these forces separately. In other words, you know the solution of the equation m r1 double dot is equal to f1 of r1. Okay, the one here in the R is purely for convenience to distinguish the two situations. This R1 is measured from some origin. The position of the particle is here. It is called the vector R. It can also be called vector R1, called vector R2. There is no, R1 is simply a name here. And you have the solution of the equation of motion mr2 double dot is equal to f2 of r2. Okay, suppose you have those two solutions and you simply add the two equations. Yeah, you will get, and you define R as R1 plus R2. This is simply a proposal. One is asking whether the trajectory passing through the location R can be obtained by combining these two trajectories. So the equation you will get is M. Any question?
So is this because this kind of equation is consistent with the natural laws?
No. The issue, the central issue here is that force is a nonlinear function of location, and you cannot add two forces in the manner you would add linear functions, simply because it's a nonlinear function. So what is this right hand side? So yeah, the question that was just asked, it's something completely different.
I think because they're linear by nature, that's why we could add them.
See, if the force was a linear function of position, then the sum of forces evaluated at the sum of locations, you would have the distribution law. But for nonlinear functions, that does not work.
Okay, sir.
Yeah, that is the central issue here.
Okay.
See, on the right hand side, what you will get is mr double dot is equal to f1 of r1 plus f2 of r2. Okay, this is what you will get. Okay, let me write this explicitly. This is then the expression alpha r1 by mod r1 squared plus alpha r2 by mod r2 squared. Okay, so this is what r1 plus r2 satisfies this equation. But the equation we really want to solve is this one, where this is equal to mr double dot. That's the equation you wish to solve. Yeah. So the question arises.
Yes, sir. Yes, sir. Got it.
You got it, Debashish? Is that Debashish?
Yes, sir. Yes, sir.
Okay.
Yes,
so
sir,
great.
yes.
Yeah. So the point is that the sum of these two functions written here is not equal to this function here. Yeah. I mean, there's an R1 here. Sorry, alpha and beta, not to mention. I mean, even if alpha and beta are the same, you still have trouble because the denominators are different. You cannot simply add these things and get this kind of formula. Okay.
Sir, do we need to take these formulas seriously, or like they are just you give to show
No,
us?
this is right now. It's only a general discussion. If you don't follow it carefully, it is quite okay. The message to be perhaps I will give a simpler example in one dimension, which then you can take more seriously. So for those who didn't quite follow what's happening here, do not despair. Take away only one thing from here, that you can't add solutions of equations of motion in the presence of distinct forces and hope to get the solution when both forces are present. That message, if you get, it is adequate. I will try to clarify it through a simpler example elsewhere, and that might help you further.
Sir, I mean, how do you come up with the formulas for F1 and F2? Like, are they relevant to some practical situation, or just you wrote some?
Oh, that's why you are asking. No, they are practically relevant. That's why I wrote them. They have to do with the gravitational force. That's why I wrote them. But that we are going to discuss soon. So we will talk about the gravitational force soon. So this was just an example motivated by physics, of course, but it was simply an example.
But in general, it is not necessary that both F1 and F2 will be pointing in the same direction.
No, it is not necessarily the case. No. Yeah, it need not be the case. See, the two forces may be very different. One may be an electric force, one may be a magnetic force. Yeah. Or let me show you this figure. Yeah. This is a concrete physical system. You have a pendulum bob that is attached to some support here. It is subject to two forces. One, gravity downward pointing, and the other that I can call my F1. And then another one, which is the tension in the rod, which points in the direction of the rod. So these two forces point in different directions. And suppose you ignore gravity and solve this problem and find some trajectory. And then suppose you ignore the tension and simply consider a particle subject to gravity, find trajectories using that. Yeah. And somehow add those two trajectories. The resulting trajectory, this resulting motion does not describe what happens when both forces are present. Yeah, you will see. In fact, let us take this a little bit more seriously. Suppose I turn off gravity. I turn off gravity and consider a particle attached to a rod which is suspended from somewhere. Now, because there is no gravity, it is going to just oscillate, move around freely. The tension will not change with time. Yeah. But the particle will be at a fixed distance from that support. On the other hand, suppose I forget about tension completely and look only at gravity. Yeah. Then the motion is completely different. I mean, a particle subject to gravity can simply fall down. Yeah. So it is not even meaningful to combine these two situations and somehow get a trajectory when both are present. Yeah. So physically, this absence of a superposition principle for solutions is very, very obvious. You simply can't add trajectories in general. But it is worth making it more precise, and I will try to do so through a simpler example. Okay. But do not despair if you didn't catch everything in the last, in the recent discussion. There is more here that we should focus on. Then I want to make one more comment, but anything from before that you feel you want to know, clarify right now. Okay. That being the case, I will make one more comment in a different direction. This is also a kind of superposition principle. So suppose, and it's related to something that was asked at the beginning of the lecture. Suppose a composite body is made up of several constituent parts. Yeah. So it could be a rigid body like a stone that is made up of several point masses. Okay. Several point masses. Then we can speak of the total force on the composite body as the vector sum of the forces on its constituents. Okay, so here's a picture. Here's a picture. My body consists of two masses connected by a, let us say, a very slender rod, which is practically massless. Okay, and that is in this room. Both the endpoints feel a downward mass force mg, each of them, and then we can talk about the total force on this system, which is simply the vector sum of these two, and I will call it 2mg. Now, there is a separate question about center of mass and through what point one may wish to think of this total force as acting and so on. These are questions one will have to address when studying composite bodies or rigid bodies. Yeah, so I don't want to go into those issues right now. But the statement is simply that just as you can resolve the forces acting on a single particle according to the origin, frictional, gravitational, and add them up, similarly, the total force on a composite body is the sum of the individual forces. That is all. Okay, so is the statement all right? Okay, okay, good. Yeah, let me then move to Newton's third law, which states the following. So Newton's third law says that, I mean, in a somewhat colloquial way, that to every action there is always opposed and equal reaction. Yes, I presume you heard such statements before. More precisely, if body A exerts a force F on body B, yeah, then B exerts a force minus F on A. So here are my two bodies, A and B. Suppose A exerts a force F on body B, then B exerts an equal and opposite force on A. Yeah, so that will be minus F. So this is what it says. In old-fashioned language, these two forces are called the impressed and expressed forces. We will not use the terminology. I'll hardly use it, but you may see it in some older books. Now, it is important to realize the following, that the third law is not needed to understand the motion of a particle subject to given external forces. So suppose we are interested in the motion of a particle, just a single particle due to gravity. Yeah, then the third law doesn't play much of a role. Yeah, if you have specified the force, you just said it is mg, g is acceleration to gravity. Yeah, then there is only one body present at some specified external forces whose origin we are not concerned with. Then the third law doesn't play any role in such studies. However, the third law is needed to understand the motion of bodies subject to interparticle forces. So, I mean, you must have at least two bodies to talk about a reaction force. Otherwise, it is not meaningful. Yeah. So, this distinction I do want to make, and it's worth having in mind, that Newton's third law really comes into its own when you have multi-particle systems, more than just one particle. Okay, I mean, examples of this abound. The sun attracts the earth with a force equal in magnitude and opposite in direction to the force exerted by the earth on the sun. Okay, so this is, we will give formulae for these forces soon. But this is an example of that. Newton's third law is very useful in many calculations. And we will see examples of that. Another instance is that suppose you have a cubical block of concrete of mass m that lies on the floor. Yeah. Then it exerts a downward force of magnitude equal to mg, where g is the acceleration, sorry, magnitude of the acceleration due to gravity. Yeah. Now here the other body is the earth itself. Yeah. On the other hand, the floor or the earth exerts an upward normal reaction force n of the same magnitude mg. Okay, so here it is. The earth exerts a normal reaction on the body, on the brick, and the brick exerts a force on the floor. Yeah, so this is another example of that. Yeah, so yes.
So weight is the force exerted by earth on the object or the object on the earth?
You have to talk about
weight of an object.
Yeah,
that
weight,
is mg.
Yeah, okay, I'm going to speak about the weight after a little bit of time. So, but no, if you're talking about the weight of the body, then it is the force that it feels, the force that the earth exerts on it. Yeah. So the, yeah.
So, sir, n should be like the force on the earth, and mg should be the force on the box.
Oh,
here in this example.
Oh, no. Okay. Maybe. All right. Okay, you're saying that my picture is a bit misleading. All right. No, look, what I was saying, I was thinking of it in the following way, that the brick exerts a force on the floor. Yeah, in the sense that if you put your finger or a hand on the floor and put a brick on it, your hand feels a certain force. Yeah, it is that force that I called mg. It is the weight of the block.
But sir,
yeah, I mean, there are different ways to think about this. Yes.
So gravitation is the attractive force. So in that sense, mg should be the force acting on the body by the earth.
Okay. All right. No. Okay. Let's talk about it. Maybe I was a bit imprecise. I have the floor and I have the block. Yeah. Okay. Let's leave the earth aside. I think that is a little bit confusing. The previous example, I really had the earth and the sun, and it was somewhat clearer there. But here I really have two objects, namely the block and my hand. The block and my hand. Now, I hope you will agree with me that when I keep the block on my hand feels a certain force due to the block, and that is equal to the weight of the block. But at the same time, there is a upward normal reaction force that my hand exerts on the body, on the block. This is what I was saying. Does that clarify? You are quite right that the gravitational force is the one that the earth exerted on the block. That is also true. It's really a question of which two bodies one is talking about here. I'm talking about the floor or my hand and the block. These are the two bodies in this particular context.
Okay, so when they are in contact, we just ignore the non-contact sense in that way.
Yeah, we are here just discussing these two bodies. Yeah. Yes. You are right that the origin of this weight may have something to do with the Earth's presence also. That is also true. But here we are just looking at this pair of bodies, the block and the floor beneath it. Yeah.
So when we talk about the floor, do we need to consider floor as the part of Earth? Like, if we consider then the
I mean,
force acting on the block and
no, look, I see the okay. I see the floor. I regard as my hand, and here is my block. Yeah, that is all. I'm not sure we should think about the floor as the whole Earth. That is not quite what I intended. I think the previous example perhaps is a little bit clearer to you, where you had two bodies.
Okay, I think
that
over
are
here the whole
separated.
system is about the box and the floor, because I think the Earth's force is totally an external force to this system. So I don't think we should consider that.
Correct. We are not considering the Earth as another.
Like there can be other forces from the gravity of moon and etc. So we are not going to consider those.
That's true. That's true. Yeah. See, we are not asking the question, why does the block exert a force on my hand? Yeah, that is due to the presence of the Earth, no doubt. We are just saying, when I keep a block on my hand feels some force. Yeah. And if my hand is not to fall down, I need to exert an equal and opposite force to support the block. That force is called N. That's all. Yeah. The block exerts a force on my hand. The magnitude of that force is mg. The origin of that force is the presence of the Earth, no doubt, but we are not concerned with the origin of that force. We are just talking about what is the force that the block exerts on my hand, and what force my hand, as a consequence of the third law, must be exerting on the block. Is that okay, Saptarshi?
Yes, sir.
Okay.
So if we suppose that there is the box and our hand is an isolated system, then the box, our hand will still exert the force on the box, but box will not exert the force on our hand. Then how is it that possible?
No, I am considering a block here in this room. So the Earth is very much present. That has created a certain force. It is just that the hand is supporting the block, and therefore the hand feels that force. That is all.
Like we consider isolated system of our body and the box. Like we are somewhere isolate, and then box will not have the mg force. So
okay, then yeah, okay. So fine. In outer space, you are considering this block and my hand. There are no forces present. There is this exerts a zero force on that. That exerts zero force on this. So that's also fine. If that is what you had in mind. If the Earth is not present, then yes, that is all there is.
Then our hand won't exert the normal force on the box.
In other words, the normal force will be of magnitude 0.
Yeah, fine.
Yeah,
thank
you are right. Yeah. Okay. So let me. I want to make a small remark, which is actually for future reference. So you can ignore it now if you wish. Yeah, so for future reference, Newton's third law also helps us distinguish between a real force and a fictitious force. Okay? So there is something called a fictitious force in frames that are not inertial, which are called accelerated or non-inertial frames. There is something called a fictitious force. Now, according to Newton's third law, an acceleration due to a real force felt by a body is distinguished by the presence of an equal and opposite reaction force on some other body. Okay. So that is the special feature of real forces, which Newton's third law applies to. It does not apply to fictitious forces. Okay, so in the case of fictitious forces, acceleration that is felt due to a fictitious force is not associated with some reaction force on some other body. Okay, we cannot use that argument there. So this is one thing that distinguishes the two. But again, this is really a remark which gets ahead of our current understanding. I just mention it here for future reference. So don't worry if you don't know what a fictitious force is. All right. Okay. So okay, I just want to make a few remarks on some terminology now. You would have heard terms like dynamics, kinematics, and statics. In brief, what do they refer to? We keep using the word dynamics. So I should say what I will mean by that term. So dynamics refers to the evolution of a system in time. Yeah, the actual motion of a system in time, the evolution of a system in time, the motion of a system due to the forces in operation. Okay, so this is called dynamics. Yeah. So it really has to do with time evolution due to forces, due to interactions. So you need to know the forces to understand the dynamics. Without that, you won't get anywhere. Now, statics is not supposed to be the opposite of dynamics. That is not the sense in which it is used. Statics simply refers to situations where a system does not change with time. Okay, so that is the name used for it. The word dynamics is not thought of as the opposite of statics. In some contexts it may be, but that is not the sense in which we use it in physics nowadays. So statics simply refers to time-independent situations, yeah, where the system does not change with time. That a fact that the system doesn't change with time is itself a dynamical fact. Yeah, it means that the forces are such that it remains that way. Yeah, so I hope the language is will become clear to you. Any question about what I said now?
So what you just said, that the fact that it is static is itself a dynamic
Consequence of the nature of the forces in operation. Yes, indeed. Yeah.
I didn't get how it is dynamic.
See, dynamics refers to how does a system behave with the passage of time. Yeah. Okay, this is the question that dynamics answers. Now, to answer that question, you need to solve, at least theoretically, you need to solve Newton's equation of motion. To solve Newton's equation of motion, you need to know what the force is. Okay. Therefore, understanding the dynamics of a system requires a knowledge of the forces, interactions, etc. Okay. Now, when you do that, you will find how the system behaves. You may discover one of many things. You may discover that all parts of the system simply stay put. They don't move at all. That is an entirely acceptable result of studying dynamics. We will say then that that is a static solution of the equations of motion. That's all. But there may be other solutions, other evolutions, depending on initial conditions, where parts of the system move around because the force is present. Simply because the parts of the system did not move does not mean there are no forces present. I mean, the very fact that I am able to support this block and it's not moving means there is some force that is pushing the block up just to counterbalance the weight due to gravity, the force due to gravity. Okay, so being time independent doesn't mean that no forces are in operation. It just means that some forces may be balanced. So Is that okay, Shakti Chauhan?
Yes, sir. Yeah. Thank you.
Okay. Okay. Very good. Yeah. Yeah. So now, in a somewhat different direction, we use the word kinematics. Again, I emphasize that these words are not sort of opposites or something. That is not the sense in which we use these words. They are not meant to be opposites. They refer to slightly different concepts. Kinematics usually refers to those aspects of a system and its motion that do not depend on the specific forces that act. Okay? So often that is the sense in which we use the term kinematics. Yeah. Kinematical aspects of a system are those aspects that don't depend on the knowledge of the forces. Okay? But they may depend on other features of the system, like number of degrees of freedom, how many particles there are, yeah, where can they move, the range of values that the physical variables can take. Yeah, if this is an angle, can it go from 0 to pi or 0 to 2 pi? Such questions. Okay. How do these values, namely the variables that you use to describe a system, in different frames of reference, how do they change? Yeah, that is also a kinematical question. Yeah, suppose you have certain values for your physical quantities in one frame, like your position. Yeah, what is it when referred to a different frame? This is again a kinematical question because it only depends on a change of frame. It doesn't depend on the knowledge of forces. Okay, so we will call that also a kinematical question. Similarly, sometimes we call the problem of finding the trajectory from the acceleration as a kinematical one. Okay, suppose you already know the acceleration, yeah, then, or you already know the momentum of the particle, then you want to find its position. Maybe you have to do an integration. Okay? That is again a kinematical question. On the other hand, finding the trajectory or the acceleration from the forces involves dynamics because it involves knowledge of the forces. It involves knowledge of the interactions present. So dynamics and kinematics are sort of complementary in this sense, that kinematics are those aspects that don't depend on the forces in operation by and large, whereas dynamics requires the knowledge of those forces. Okay, so is this terminology understandable? Any question about it? Okay, in that case, I think we've come to the end of the allotted time for this lecture. We shall then continue next week, but I shall be in touch with you. Please do submit your assignment tomorrow afternoon, tomorrow evening. Any last minute questions now? Okay. Yeah, there are parts of today's lecture which may have been a little bit difficult to follow and things which are incomplete, which I will fix up. So not to worry about that. Okay, good luck then, and have a good afternoon.
So
yes, yes, Rupunjay, yes.
So now am I audible?
Yes, you are.
Yes, sir. So what I was asking is, like, in the beginning you showed that if you have r double dot plus r triple dot or something of that sort, then basically like it can be shown to violate the fundamental idea of force, which is to cause acceleration, right? It defines something else but not force.
No, I would like to clarify that my intention was to consider that equation and ask whether particles in the absence of forces would follow straight line trajectories or not. And if they did not,
yes, sir,
it would violate Newton's first law. That was all that
yes,
the
sir.
intention was. Yeah.
Sir, and like so in that case, I have a more generalized version of this thing, sir. So over here we have only talked of acceleration, like of sum of two different orders, right? Let us assume we have a random function, whichever way we want to have it, like, and that will be third degree, say double dot and triple dot, both are involved. Now to solve a third degree equation, you need three initial conditions. We can impose one of the initial conditions for zero force to be, say, r double dot equals to 1. We can do it, and in that case we'll be able to solve it, and that verifies the fact that this will always be like there will be a case which falsifies the that thing. So we can not have two terms irrespective of the form of equation, no matter which kind of equation we choose, because the initial condition can be set.
Yeah, if I understand you right, see, I think you're on the right track. See, I propose an equation, and all one needs to show that it admits one solution. Yeah, with whatever initial condition you pick, you have to only display one solution, which is not a constant velocity solution. Now, I tried to give an example, and I did a calculation mistake in that. I just need to provide one more solution, which is not a constant velocity solution, and that
Sir,
will
and
violate.
this can be done.
Yeah. Yeah. So
So
yes.
this can be done for every case, like for every form of equation. Put the initial condition to be r double dot equals to 1 for force equals to 0, and we can
Okay.
solve it then. And we'll have a solution.
Okay, sure. Yeah, I mean, I have to look into that. But yeah, I do believe that you can choose initial conditions such that the trajectory will not be a constant velocity trajectory. Yes. Yeah, perhaps the specific case you suggest will
and
help.
sorry for extending it, but another
Yeah.
thing.
Yes, please.
So sorry for like extending the thing, but another thing. So I have this argument of involving homogeneity in this thing. So because we have r double dot and we have r triple dot, right? So there will be an extra dimension of time that is in the denominator, which will be accounted in terms of k. So the k will have dimension of mass times time. Now body already has a property of mass and already has a property of time. Say it is universal, it doesn't depend on mass and time. In that case, how do you find the value of k? Because say like how do you find it? You can't set your values in a way, like because capital G was found by setting mass to be some measure, right? It can be scaled. The constants can be scaled. So you can't predict a value of k. And in that case, it should not be universal. And if it is not universal, it will involve time. So homogeneity principle can also be used in a vague sense, not exactly.
No, I am not very sure I catch what you're saying. See, homogeneity in time simply says this equation is time translation invariance. The equation that we proposed, namely mx double dot plus nu x triple dot equal to 0, is time translation invariance. Namely, if you replace t by t prime, which is t plus constant, the equation will not change because d by dt is equal to d by dt prime. Because yeah, I mean, you check this because what is this? Yeah, d by dt prime is, according to calculus,
Yes,
the
sir.
chain rule, d by dt times dt by dt prime. Now dt by dt prime is equal to 1. So the two
One, yes,
derivatives
sir.
are one and the same, and therefore the derivatives with respect to t and t prime are one and the same. So this equation is time translation invariant. You are addressing a different question, namely what is the dimension of this nu? It is, yes, you will, if you are going to consider such an equation, then nu has to be a new dimension, a new dimensional constant that has to be
But
introduced.
sir, shouldn't it have the dimension of m into t? Because x
Correct,
double dot is
correct,
being added to m,
correct,
right?
correct.
So
Yeah.
how do you
So
and right?
that in itself doesn't violate time translation invariance. So I want to distinguish these two
Yes, sir.
constants. So you are
Yes, sir.
saying
Yes, sir.
that it
So
may be difficult to find a constant of that sort. Sure, maybe yeah. I mean, if you propose such a thing, then you need to get the physics of that also. But yeah, you are right. But no, we cannot appeal to time homogeneity in time to cancel that term out.
So the reason that I say this is we will have to depend on mass and time, right? And we don't know any other property than mass and time, right? These are the two most fundamental properties of time. So how do you make a quantity which is local to a body and depends on mass and time without explicitly depending on time or time difference? And even if it is time difference at a point, so all those things, the initial condition will come into the picture and things will depend on the local explicit time, like explicitly on time.
No, I don't know if I follow that. I mean, nu could simply be a constant, and that is to be determined experimentally, just as we would have to determine the mass of a particle through measurements. So I don't see why we are not saying that nu is an explicit function of time. You are talking about the dimension of nu, and I would not like to confuse the dimension of nu to time dependence. These are slightly different issues.
So let us consider this equation. I have mx double dot and this is equal to some gravitational force. How do I set the value of g? How do I find the value of g? Double the unit of mass. Basically double, like scale the mass to 2 times of its current value. Then the value of g is automatically halved. So we set the value of constant by choosing one system for one of the things, right? We have already chosen a system for mass and we have already chosen a system for time. So right, nu has to somehow respect those things. And so if it is respecting those things, then what is the relationship which is coming into the picture? That is what my question is. Like,
No,
so
I
in that
think, see, okay, your question has something more to do with dimensional analysis. See, you are saying that now we have yet another constant in our system with that have the same dimensions as existing constants. Can it, if you choose units where other constants are measured in a certain way, does that put constraints on this? The answer is no, because you can have dimensionless constants in your theory. Yeah, so there is it does not restrain you from having additional constants. Yeah, I think the key point that you have not addressed is that a model can have dimensionless parameters.
so, but over here it
Yeah.
has to have the dimension of time and mass.
Correct. Nu is a dimensionful quantity, but you are saying, suppose you pick units where something else is something and so on, where the masses are measured in kilograms and lengths in meters and time in seconds. Yeah, that itself does not mean that you can't have an additional constant nu in your model. That does not prevent it.
So, but like but then like if it is something like an universal constant, which is independent, which explicitly is independent of mass and time, which is something of its own.
No, we are
then
not
how do you
saying,
find it?
No, we are not proposing that nu is a universal constant. Nu is a property of that particle which you are studying. Just like the mass is the property of the particle, this is some new property of the particle. Yeah, I am not saying that property exists. We are trying to argue why this cannot be the case using the laws of Newton. That is all we are trying to do here. I do appreciate that you are trying to argue why such a term cannot exist based on some other dimensional argument or other type of
Excuse
knowledge.
me, sir.
Yeah. So, but I think it's a different type of question.
We can use another argument that Ripunja said to falsify it. I mean, you could express mass in terms of the dimensions of nu, and then mass will have a dimension of time in. And then if Ripunja's argument is right, then mass will not exist. So this is a wrong argument.
See, parameters in a model
but then
can
nu
have
will
dimensions.
exist, right?
But see, I think we are climbing the wrong tree here. It is not as though a parameter model cannot have dimensions that include time in it. That is not forbidden at all. Yeah.
Yes, sir.
Yeah. So that is, we should not take that viewpoint. There is nothing that forbids. I mean, a force constant in that describes a spring includes a time dimension somewhere, right? It is some force per unit length. So I mean, force includes a time unit somewhere there. So this is not forbidden at all.
So, but that time unit is coming from difference, like infinitesimal difference between time instant, right? This and the next instant, and that remains invariant no matter which time you specifically choose. My thing is, how do you find out nu if it exists? Like if it exists, let us assume it is there. Now, how can we find it out? Like there is no way you can find it out, because if you choose a different scaling factor for mass, then this will be affected in a way.
No, I don't think that is the case. Suppose one can justify such an equation. How do you fix the parameters in the equation? Well, you find the solutions of this equation, you compare them with the corresponding observed motion, fit the two parameters to match it, and what you get is what you get. That is how one proceeds. These are called parameters in the model, m and nu. You find solutions with given initial conditions, compare the trajectory with the observed trajectory that is described by this equation, and thereby fit the parameters. It is not a problem if the parameters include a dimension of time and so on. That is not an issue.
So like you have two variables in one equation. No, right?
That is not true. We have a differential equation having two parameters, m and nu. It is this is a differential equation. A differential equation can have any order. Here it happens to be a third order differential equation with two parameters. Look at it this way. I have a model for nature involving two free parameters. Yeah. I find predictions from this model depending on those two free parameters, and the job of a physicist is to compare it with the experiment and fit it to the results from experiments to determine those two parameters to the best possible in a reasonable fashion. If the model has three parameters, that's also fine. It is just that more parameters that a model has, the less predictive power it has. That one can say.
So the thing that is troubling me over here is like length and mass are free parameters or time is a free parameter, but
No,
all
I
of them
do
have
not
different
agree with that
dimensions.
statement at all. Length, time, and mass are not free parameters. Length, time, and mass are certain dimensions. We will not call them free parameters at all. M and nu are free parameters which are to be determined through experimentation. Please be careful with the terminology. Length, mass, and time are not free parameters. They are simply dimensions of physical quantities. That is all.
Okay, sir.
Yeah, perhaps we will come to these issues again and again. And but I very much appreciate your questions, and I hope others are also benefiting from it. Yes, last question. Yeah,
sir, about that question which
yes, please.
About that question which I asked in the beginning,
Uh-huh.
Can you just give the in notes only? Can you give the working on how that thing will work out? I mean the working.
Which question was this? Sorry, once again. Could you repeat the question?
If we write force. Excuse me, sir.
Yes, please speak up, Shubham Kumar. Yes.
Yes, sir. So if we write force in terms, I mean, for a system of particles in which mass is varying, I mean, you set that and then work out the Galilean invariance. I mean that. So that working.
Consider center of mass.
Okay. All right. You are saying if a system has a variable, an object whose mass is not constant, to treat such systems, like a rocket that is expelling some gas or something like that.
Yes, sir.
Yeah. Okay.
That just, I mean, I could not do the working out there.
Okay. 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 Maybe an example would help. Yeah.
So, sir, in this case, can we do it in this? Can we consider the center of mass, and then like for center of mass, the mass will be constant, right? So for any system with variable mass, the center of mass will be there. Because second law can be used to formulate the third law, and then once you have your third law, you can come back and like use that argument.
Your suggestions may help, yes, but no, I think, see, the point is, I think the question itself is not formulated clearly, so it is hard to answer it. And what is the system you wish to consider? And then one can speak clearly about it. Yeah, I mean, there are problems in books about rockets which are expelling gases, so one can certainly study that kind of system. That does not violate the idea that a single particle has a mass that doesn't change with time. It's just that its material is being expelled, and therefore you need to account for that. And I think the problem arises when you want to write an effective Newton equation for the whole system. Somehow incorporating these kinds of things, one needs to be a little clever. Yeah, it doesn't invalidate the fact that a mass of a particle doesn't change with time. Yeah. But okay, we'll look at an example of that sort, if that'll help. Okay, perhaps a concrete example will be more helpful there. Okay, so by and large, we have been talking about single particles or a system of point particles. That is different from looking at a composite body whose amount of matter itself is changing with time. Yeah. So then things, you have to deal with that composite body more carefully. That is all. One should not confuse it with the invalidating Newton's law for a point particle. These are different issues. Okay. Any other thing at this stage? Okay. Yeah, anyway, if I understand Shubham right, you want to look at some example where the mass of a system is changing with time. Is that right?
Yes, sir.
Okay. Okay. An example of such a sort. Fine. All right. We'll think of something. All right. So if there isn't any other immediate question, we will end this lecture and meet next Tuesday. All right. thank you, and have a good afternoon.
Thank you, sir.
Thank you. Yeah.
Thank you, sir.
Yes.